Hi, this is Alix Paultre with Aspen Core Media, and I'm here with my friend Bernd Neuner and J.C. Sun, and these guys are very good test and measurement experts. And the reason that I'm here is I'm at the Power Forum in Munich right now for Aspen Core, and one of the things about wide-bandgap semiconductors is it's putting a lot of stress on the passives and the magnetics, isn't it, J.C.?
Right. The bottleneck is much more of stress on the magnetic components for the high-frequency magnetic, for the high-frequency application. This is going to be more and more in stress. Yeah.
Exactly. When there's a lot of pressure, I mean, the faster you push the board, the harder you push the devices, you got to have better passives and magnetics, right?
Absolutely. People totally underestimate that. You see all the advertisement for the MOSFETs, SiC and GaN, and all the rest falls by the wayside, and you only find out the hard way if they're not up to the job.
Well, exactly. So you've got devices that are pushing theoretical maximums, and then you're putting them next to magnetics that may not even be qualified for that application space, right?
Right, because people don't know how to do it. They try to reuse some legacy stuff, and they go by experience, they go by intuition maybe, but they don't go by hard science yet, and that's what we advocate.
Yeah, exactly. So, JC, tell us a little bit about this, because it's kind of a joint endeavor here, right?
Yeah, sure. I mean, with the increasing frequency, not only to do with the magnetics, we have to do with thermal dissipation. Substantially, their thermal dissipation is going to be a mechanism what people need to deal with. And the passive components in the past, it's not stressed in that context, and that's something need to be studied. And I think in the good sake of the applications, in good sake of the efficiency, it's a necessity actually. And we are, for the power electronics, we are going to talk much more the multi-physics domain optimization process. But for the magnetic people, they're totally different. And this is going to be sensitized if we can emphasize, enhance the competence on the measuring science. Yeah.
Well, and so now, tell us a little bit about this equipment here, because this is obviously directly engaged in that kind of qualification, right?
Yeah, when you look at what it takes to precisely measure magnetic losses, you'll find out that a power analyzer is already optimized by design exactly for this task, because what matters is supreme accuracy, supreme resolution, and minimal phase error, an excellent relationship between voltage and current signal.
So now, walk me through it a little bit. I'm an engineer. I'm trying to, speed my board up and trying to get my efficiencies up. What do I need to know to appreciate this?
Well, when it's about qualifying magnetic components, there's a simple way. Because in the past, all the IEC standards call for a very sophisticated signal to stimulate, and a rather simple way of data acquisition. What we advocate is spending a little less money on the signal, and that makes sense anyway, because in real life, no magnetic component is ever going to see the signal that's specified in the IEC standard. That is a perfect sine wave. It's going to see some brutally chopped up PWM signal, and that's what we can use in our approach to smart measurement.
Very nice. Can you elaborate on that, JC?
Yeah, absolutely. I can emphasize on this. First of all, the characterization for magnetics, magnetic material. There is standard. You need to confirm the standard, and this is one of the layer of the problematic. The others is that the standard is not suitable to describe the activation for the power electronics. And I would like to sensitize there is a difference between the performance of the instrument and the performance of systems. So, and we are actually in Europe very well equipped, because we established the standard in late 90s. Well, right now the challenge is much more that how can we make such kind of a robust standard for the magnetic components. And for and this is a big, tough challenge, and this we are going to strive for that way. That's neat paradigm changes, and we are going to sensitize this.
Right. So now tell me a little bit more about your solution, about BS&T solution. How does that apply to what the engineer is trying to accomplish?
Yeah, this is, for instance, the BST systems. It consists of the instrument. Could be a scope. It could be power analyzer. Could be power meters, and then the signal is going to be linear amplified and biased with DC, and the excitation of the device in the test is going to be critical. And there's a lot of reasons why people are doing with sinusoidal magnetization. Then people can address the shift only to the phase shift. And this is again the question from the audience, that how to do the D-screw, and people certainly can do different ways, but how to control, how to manage the voltage current decay. This is something might be not trivial. And that is actually a different word for the magnetic people society. The other thing is that with the ever increasing DC current, and you cannot emphasize all the strategic. This is something like the pulse method and bipolar excitation, actually to test the magnetic components right in the constitution, right in the context which is applied under real conditions. That's going to be used different methodology, and this is something that we're going to sensitize in the audience.
So, and what device do you have here? What's the model number so that people can look it up?
Yeah. So the model number is here is a BST Pulse 1K and 3K. 1K, the first 1K is associated by the the loaded voltage level is in 2000 volt, and 3K means if you short circuit, and then you can reach with one pulse with some 3000 amps, and 3000 amps is the people really want to see for the traction, for the data server, and for the fast charging, for instance. Yeah.
So now, Bernd, what about your devices? Can you give us a couple of model numbers of some of the products they can look up?
Well, basically we have the family of the LMG 600 power analyzers, the most prominent one being the 671. And I've spoken to many people at this conference, and how we make their lives a lot easier is, yes, you can measure certain electric parameters like the peak current on the primary, the rectified voltage in the secondary, and then do all the math yourself. But these modern power analyzers, they're like chameleons. They can behave like any sort of instruments. I can easily turn this into a magnetic loss tester. So you measure voltage and current, and you display peak value of field strength, magnetic flux, losses, and all that. So the instrument does the math, and you don't need to be an electronics design engineer to get readings of your device under test.
Very nice. So, JC, before I let you go, do you have any final words for our audience to talk about your product or send them to the website or something?
Yeah, well, I think that's, I appreciate very much, Alex, you help us very lot and try to sensitize a very important topic in this power electronics society. And for the magnetics components side, there's not only the measurement, the first thing. The secondary thing is much more for encourage people to get more emphasis of material development and
pay more attention to the magnetics and passives.
Right, exactly.
How about you, Bernd? Last words?
Same words as always. Don't blindly trust. Measure. Only after measuring you can trust, not before.
There you go. So thank you all for taking the time to be with us today.
Thank you.
Thank you.